Hello there. Once again, I would like to welcome you to PS 1.618. In this video, and a few others that are going to follow, I'm going to be discussing ideal gases and thermal properties. An ideal gas can be defined as a gas that obeys all gas laws under all conditions of temperature and pressure. This chapter is going to be divided into 3 units. The first unit is going to discuss the kinetic theory of gases. Unit 2 is going to be looking into ideal gas law, and the third unit is going to be looking into temperature, heating and pressure. These are the unit goals for the kinetic theory of gases. By the end of this unit, you should be able to describe the motion of individual particles of a gas by saying that particles of a gas collide with each other and with the walls of their container. You also need to be able to describe the motion of individual particles of a gas by saying that molecules of a gas move at different speeds. Number 2, you need to be able to explain the idea of average speeds in the context of particles of a gas. Number 3, you need to be able to describe an ideal gas in terms of the motion of molecules. Number 4, you need to be able to explain how a real gas differs from an ideal gas in terms of the motion of the particles. Number 5, you need to be able to state the conditions under which a real gas will approach the behavior of an ideal gas. Number 6, you need to be able to use kinetic theory to explain the gas laws. Let us begin. What is the kinetic theory? Well, the kinetic theory of gases is a theory that is used to explain the behavior of gases. So, to explain why gases behave the way they do, we're going to be using the kinetic theory of gases. We need to understand, first of all, that particles of a gas collide with each other and with the walls of the container. Let us look into the following simulation to understand what is meant here. Let us look into this container here, which is having particles which can be taken as particles of a gas. Now you can see that the particles continually collide with the container or the walls of the container, and at the same time, every now and then, they're going to be colliding with each other. The kinetic theory of gases is based on the following assumptions. Number 1, the particles of a gas move in straight lines except when they collide with each other and with the walls of the container. So we are saying that each and every particle that we're having here, which is a particle of a gas, is going to be moving in a straight line. There is no way that it is going to change direction unless it collides with another particle or unless it collides with the wall of the container. Number 2, the molecules of a gas are so small that they occupy zero volume. We are saying in many practical situations, the molecules of a gas are very, very small compared to their container. And because they're very, very small compared to their container, we can practically say that their volume is negligible. In other words, their volume can be ignored. And that's what we're going to do in this chapter. We're going to be ignoring the volume of the particles. And that is because they are so small compared to their container. The other point that needs to be made is that there are no intermolecular forces between the particles of a gas. But the intermolecular forces will start to act only when the particles collide. So we are saying that for as long as the particles are moving and they do not collide, then between them we do not have any intermolecular forces whatsoever. In other words, the particles do not repel each other, the particles do not attract each other. There are no intermolecular forces between the particles. They will only exist when the particles do collide with each other. The last point is that the collisions of the gas particles are perfectly elastic. And what is meant by that is that when the particles of a gas collide, the total kinetic energy that they were having before they collided will be equal to the total kinetic energy that they will be having after they've collided. Now in gases, we will be working with the average speed. So we will not be working with the exact speed of each and every particle that we're having inside a container. Now this is because the particles of a gas all move at different speeds and in random directions. So it will not be easy for us to determine the speed of each and every particle that we're having there. But we can get an idea of the average speed of gas particles by measuring the temperature of the gas. Now let us look into this simulation in order to understand what is meant. Now let us say I had as many as this number of particles there. We can clearly see that they are all moving in many different directions and they've got different speeds. If you look into this one, for example, it's moving slower than the other red particles. Now that says if you're having many particles, they'll be moving at many different speeds and in different directions, and therefore it will not be easy for us to determine each and every value of the speed for each and every particle that we're having there. And therefore we do not work with the exact values of the speeds, but we work with the average speed. And we can have that value or have an idea of what the average speed is by measuring the temperature. Now it should be easy to understand that, because if we increase the temperature by heating maybe the gas, then we see that the particles will begin to move faster. Now if the particles are moving faster, then that means they're having higher speeds, and the average speed is also going to be higher. So we can clearly see that a higher temperature refers to a higher average kinetic energy or a higher average speed. So if we lower the temperature by cooling the gas, for example, then we see that the speed of the particles, or the average speed of the particles, is going to become smaller. And as you can see, the temperature is lower than the one that we're having before, and the particles are moving slower than they were moving before. Now let us talk about the physical quantities that we'll be working with in this chapter. The first one is pressure. Pressure is the force per unit area. In terms of an equation, P is equal to F over A, where P, or small letter p, is pressure, F will be the force exerted, and A will be the area where the force is acting. Now we have pressure because of the many frequent collisions of the particles of the gas with each other and with the walls of the container. Now if we look into this simulation here, there are many collisions that occur at each point in time, and because of that you have what is called pressure. If you're having many collisions because of many particles, then you see that the pressure is going to increase. Now the pressure exists because of the collisions between the particles, or the collisions between the wall of the container and the particles. Now pressure is measured in Pascal, PA. The pressure of a gas will depend on the following. Number one, it will depend on the temperature T of the gas. Temperature is a measure of the average kinetic energy of the particles of the gas. Like we've stated earlier, a higher temperature means a higher kinetic energy, or a higher average speed of the particles. As you can see here, we're having a higher temperature and the particles are moving faster than they were before. If we decrease the temperature by cooling the gas, then the particles are going to be moving slower and the value of the temperature is going to be smaller. Now, that is because when we're talking about temperature, we're simply talking about the average kinetic energy of the particles or the average speed of the particles. Now, temperature is measured in Kelvin, capital letter K. The higher the temperature, the faster the particles move, which will result in more collisions and a higher pressure. Now, we are saying that pressure depends on temperature in the manner that an increase in temperature is going to result in an increase in pressure because the particles are going to be moving faster where the temperature is higher, and that's going to result in more collisions and therefore a higher pressure. The other thing that pressure will depend on is the volume of the gas. The volume of a gas is the amount of space occupied by the gas. It is measured in cubic meters. The smaller the volume, the less space is available for the particles to move, leading to more collisions per second and a higher pressure. Now, if you check this container here, we can be able to increase or decrease the volume. If we increase the volume, then the particles here have got more space to move, and that's going to result in less collisions per second. But if we decrease the volume, making the volume smaller, then there are going to be more collisions because the particles are going to be having less space where they can move, and that's going to lead to more collisions and a higher pressure. The other quantity that we're going to be dealing with is the amount or the number of moles of a gas. We refer to the number of moles of a gas as the amount of molecules of a gas measured in moles. The higher the amount, the higher the pressure. Now that should make sense because if we increase the amount by adding more and more particles, then more collisions are going to occur since now you're having more and more particles, and that is going to result in a higher pressure. To simplify things for ourselves, we make use of an ideal gas. Now let us compare ideal gases and real gases. First, we're going to define what is meant by an ideal gas. An ideal gas is a theoretical gas that obeys all gas laws under all conditions of temperature and pressure. In other words, an ideal gas is a perfect gas that will obey all gas laws, and it doesn't matter what temperature you are having or what pressure you are having, it will always obey all gas laws. Now, we're using the word ideal here in the sense of perfect, but then there is no ideal gas, there is no perfect gas. So an ideal gas is only theoretical, it doesn't really exist. Now, what are the properties of an ideal gas? Now, if the ideal gas existed, then we'd expect that it would have the following properties. Number one, all particles are identical in all ways. The particles of an ideal gas will occupy no volume because they're very small compared to their container. Number three, they exert no forces on each other except when they collide. Number four, they collide perfectly elastically. Now, what is the difference between an ideal gas and a real gas? Real gases occupy volume at high pressure and low temperatures, but we said that for ideal gases, the particles of an ideal gas occupy no volume, and that will be the difference between an ideal gas and a real gas. Another difference is that real gases exert forces on each other, but we've stated earlier that ideal gases exert no forces on each other, and they only do that when they collide. Now, we have said that there is no gas that is an ideal gas. In other words, there is no perfect gas. But hydrogen and helium can get very, very close to behaving like an ideal gas. And that will happen at standard temperature, which will be 0 degrees Celsius, and pressure, which will be 101.3 kilopascals. So around these conditions of temperature and pressure, hydrogen and helium will behave like ideal gases. Now, this is because hydrogen and helium are very, very small. And you know this because hydrogen is the first element in the periodic table with an atomic number of 1, meaning that hydrogen has got 1 electron and 1 proton, making it very, very small, and that allows it to behave like an ideal gas at these conditions. Helium is also quite small. The other thing is that the helium atoms do not bond with other atoms. So they remain with the way they are, and they are identical in all ways. And that is what allows helium to behave like an ideal gas. Let us now go to Unit 2 and talk about the ideal gas law. Before we can talk about the ideal gas law, it's important that we handle the gas laws one by one. The first one that we're going to look into is Boyle's law, which is stating that the volume of a fixed amount of gas is inversely proportional to its pressure, provided that temperature remains constant. In symbols, you can write V alpha 1 over P, which means that as the pressure increases, then volume will decrease, or as the pressure decreases, then the volume will increase. And that will only apply when temperature is constant. So if you keep temperature at the same value, the volume of a gas will increase with a decrease in pressure, or the volume of a gas will decrease with an increase in pressure. If the pressure is doubled, the volume is going to be halved. If the pressure is halved, then the volume is going to be doubled. Now we can convert the relationship into an equation by introducing a proportionality constant K. And when we do that, PV will be equal to K. Here in this equation, P is the pressure of the gas, V is the volume occupied by the gas, and K is the constant of proportionality. We can represent the relationship between volume and pressure graphically in this manner. We are saying that the volume of a fixed amount of gas is inversely proportional to its pressure. Now that means when the pressure increases, the volume should decrease, and that's what this graph means here. As we go to the right, the pressure is increasing, but as we go down on this line here, the volume is going down. In other words, as we go from left to right on this graph, the pressure is increasing, but the volume is decreasing. You get this kind of a shape when you're plotting volume against pressure. But if you plot volume against 1 over pressure, you're going to get a straight line like this one here. Now when you do that, then the units for pressure are not going to be pascals anymore, but they're going to be 1 over Pascal, or Pascal to the power negative 1. Let us now talk about real gases and try to apply them in Boyle's law. Now at high pressures, you find that real gases do not behave like ideal gases. And that is because the molecules exert forces on each other, and the molecules are going to start occupying volume, which is going to add to the volume between the spaces of the particles. And that's going to lead to a higher volume than what is expected. In other words, at high pressures, real gases are not going to obey Boyle's law. And we can represent the relationship between volume and pressure graphically for an ideal gas in comparison to a real gas. The solid graph that we're having at the bottom, which is black in color, represents an ideal gas. The graph at the top, which is red in color, represents the relationship between volume and pressure for a real gas. Now we can clearly see that when the pressure is low, then the two graphs are directly on top of each other. This means that at low pressure, a real gas will obey Boyle's law. The pressure is going to increase with a decrease in volume, or the volume is going to decrease with an increase in pressure. But when the pressure becomes very high, then an increase in pressure is going to result in a higher volume than what is expected, and therefore the line for volume versus pressure is going to be above the line for volume versus pressure for an ideal gas. We can also plot the same relationship, but now plotting volume against 1 over pressure. Now what will happen there? We are saying when the pressure is high, which is what we're having here we're having a higher pressure, and as we go to the right, the pressure is decreasing, and it's decreasing because here we're not representing pressure but 1 over pressure. So at high pressure we expect a higher volume than what is expected, and that is why the graph is at a higher value here, and it's above the solid line, which represents the behavior of an ideal gas. Let's now talk about everyday examples where we apply Boyle's law. Number 1, if you fill a balloon with air, seal it and compress it very hard, the balloon will eventually burst. This is because compressing the balloon is going to decrease the volume and increase the pressure. The balloon will eventually burst because of too much pressure exerted on the walls of the balloon. Number 2, when we breathe, we exhale by compressing our lungs. When we do that, we decrease the volume of our lungs and increase the pressure exerted on the particles, which are basically the particles of air. Now if we increase the pressure, that's going to force the air out. Let's now formulate an equation that we can use under Boyle's law. If we have a container with a fixed amount of gas, let me say that is my container. And let me say the volume of this container here has got a volume V1, and the pressure, I'm going to call it P1 as well. Now if we increase the pressure by decreasing the volume, then we expect that the second diagram that we're going to have is the one where we are having a smaller volume. Now we're having a new value of volume, and we're going to call it V2. The pressure is going to be called P2 as well. This one is the container before, and then this one will be the container after. And of course we're having some particles of a gas there and there as well. We know from Boyle's law that when we're having a bigger volume like the one that we're having here in the first case, then the particles are going to occupy more volume and the pressure is going to be small. But if you decrease the volume, the particles are going to be closer and the pressure is going to be high. But then we've said that temperature temperature and the amount of the gas remains constant, and that's what we represent with the KD. So for the container before, we're having a pressure P1 and volume V1, so that will be P1 V1 is going to be equal to K, where K is the quantity that we are keeping constant. After changing the volume, then we're going to have a different value of volume, which is going to be V2. Then at the same time, we're going to have a new value of pressure, which is going to be P2. Now P2 V2 is going to be equal to K, and K, remember, is the value that we're keeping constant. Because K is constant, it means P1 V1 is equal to K, P2 V2 is equal to K, and we can say that P1 V1 is equal to P2 V2 because both of them are equal to K. And that will be Boyle's law equation, and this is the equation that we're going to have to use when we're having a change in pressure causing a change in volume, or a change in volume causing a change in pressure where temperature is constant. So this equation is only applicable when temperature is constant. Let us now look into exam type questions. Let me start with number 1. As you can see here, this one is a multiple choice question. 4 possibilities are given as answers to the following questions. Indicate the best answer. Write only the number and the letter that corresponds to the correct answer. 1.1. Which one of the following properties of a fixed quantity of a gas must be kept constant during Boyle's law investigation? Is it A, the density, B, the pressure, C, the temperature, or D, the volume? Well, we know that when we're talking about Boyle's law, we are basically investigating volume against pressure. Now, for the quantities that we mentioned earlier, we normally talk about pressure, volume, and temperature. If we're investigating pressure against volume, then that means the temperature must be kept constant. So the answer to our question is C. Temperature must be kept constant. Now, density has got nothing to do with Boyle's law. Boyle's law doesn't say anything about density. B. Pressure is affected by the volume, or the volume is affected by the pressure, and that's what we're investigating. We want to see the relationship between pressure and volume, and therefore we cannot be able to keep pressure constant. What about volume? If we keep volume constant, that means the pressure will not change, or if we keep pressure constant, then the volume will not change, and that is not going to help us because we want to see the relationship between volume and pressure. Therefore we cannot keep volume constant. That means A, B, and D are incorrect. The only correct answer here will be option C. Let's go to number 2. True or false item. Indicate whether the following statements are true or false. Write only true or false next to the question number on the answer sheet. If the statement is false, write down the correct statement. 2.1. Real gases deviate from ideal gases at high temperatures. Well, we know that is false. And it is false because we know that real gases deviate from ideal gases at low temperatures. And we know that because at low temperatures, that is where the particles of a real gas are going to be moving very, very slow, meaning that the intermolecular forces are going to start to affect the molecules, and therefore they're going to occupy volume, which is going to make them disobey Boyle's law and deviate from the behavior of an ideal gas. Therefore, real gases will deviate from ideal gas at low temperatures, not at high temperatures. Let us go to the third question. Consider an ideal gas kept at a constant temperature. Which one of the graphs below best represents the relationship between volume and pressure? Well, we've been told that temperature is constant. If we're keeping temperature constant, then it should come into your mind that we're investigating the relationship between volume and pressure, and that will be Boyle's law. Now we know for Boyle's law that volume is inversely proportional to pressure. In other words, when the pressure increases, volume decreases. We have to look for a graph where an increase in pressure causes a decrease in volume, and the shape that we should be having is a hyperbola. If we look into option A, this one is incorrect because this one is basically implying that pressure will increase with an increase in volume, or a volume will increase with an increase in pressure. Therefore, it's out. If you look into option B, well, this one doesn't have the shape of a hyperbola. The shape that would be having should look something like that, not this one, and therefore that one is out. If you go to option D, you can see that the volume is constant but the pressure is increasing. But we know that for Boyle's law, pressure and volume are investigated, and temperature is the only quantity that is kept constant, not the volume, and therefore option D is out. The answer would be option C, where an increase in pressure is going to cause a decrease in volume, and the shape of the graph that you're going to get is a hyperbola. We have talked about the relationship between pressure and volume, but now you can ask yourself again a question as to whether there is a relationship between volume and temperature. Well, there is. Charles' law summarizes the relationship between volume and temperature at constant pressure. Charles' law states that the volume of a fixed amount of gas is directly proportional to the absolute or Kelvin temperature of the gas at constant pressure. This means the volume of any fixed amount of gas will increase with an increase in temperature and decrease with a decrease in temperature. If you double the temperature, you expect the volume to be doubled as well. If you halve the temperature, according to this law here, we expect that even the volume should be halved. Now in symbols, we can write V alpha T, which means the volume is directly proportional to temperature. And you have to remember that when we say volume is directly proportional to temperature, then pressure must be kept constant. And to make that an equation, we have to introduce a constant of proportionality, just like we did when we were working with Boyle's law. So this will become V over T is equal to K. If you want to represent that graphically, then you can draw a straight line that will be having a positive gradient, because an increase in temperature should cause an increase in volume, and that's what this graph here with a positive gradient means. Now let's talk about real gases and Charles' law. At low temperatures, real gases move very slow, and this will cause the spaces between them to be relatively small. This will cause the volume that is measured to be higher than the value that is expected if the gas was behaving like an ideal gas. But because it's behaving like a real gas, we record a lower volume than expected, and therefore at a low temperature, where a real gas will disobey gas laws, the recorded volume will be lower than the volume of an ideal gas at the same temperature. And that would be because the particles move very slow, the intermolecular forces start to act between the molecules, and that's causing them to have a lower volume than expected. Now, the above graph that we got here, this graph here, is not what was obtained when the experiment was performed. As a matter of fact, the graph that was obtained looked like this. In other words, the line could not be extended to touch the x-axis, and that is because the apparatus that they were using there were not enough or were not capable to allow temperatures very, very low, or volumes that could go as low as 0. But now what can be done is to draw a line backward that will extend this line back so that it touches the x-axis. Now when we do that, when we extend this line backward so that it touches the horizontal axis, we say that we are extrapolating the line. Now when we do that, we find that this line is going to touch the horizontal axis at negative 273 degrees Celsius. Because at this value the volume is equal to 0, we can then say that at this temperature, at the temperature of negative 273 degrees Celsius, the particles of a gas will occupy 0 volume, and the whole gas will be having no volume at all. And that means that there will be no spaces between the molecules, and that the particles will not be moving at all. And because they will be not moving at all, we call this temperature the absolute temperature. And that is why we introduce the Kelvin, because the Kelvin is a true measure of temperature, because it is not equal to 0 when water freezes, or it is not equal to 0 when the volume is at that value. But the Kelvin is 0 when the volume is 0, which means it is a true measure of temperature, which is the average kinetic energy of particles. Now, if particles are not moving, they will be having 0 volume. Or if particles of a gas are not moving, the gas is going to be having a 0 volume. And that is what this graph here represents. On the other hand, the graph that we obtained here, the graph that was obtained from the experiment, didn't show that at 0 degrees Celsius particles have 0 volume. As a matter of fact, it shows that at 0 degrees Celsius particles or the gas occupies a certain amount of volume, which doesn't really go with the definition of temperature that says temperature is the average kinetic energy of particles, which means if particles are moving, they should occupy volume. If particles are not moving, then they do not occupy any volume, or the whole gas doesn't occupy any volume. Now, if you plot the graph of volume against temperature using the Kelvin temperature scale, then we're going to find that the line is going to pass through the origin, and it's going to have a positive gradient. We can use the following equation to calculate volume or temperature depending on what we're given for Charles' law when pressure is kept constant. So this equation only applies when pressure is kept constant. What are the everyday examples that are observed where Charles' law is applied? A partially inflated soccer ball will expand slowly and will eventually look inflated when exposed to heat from the sun, and that is because heat from the sun will cause the temperature of the air, which is the gas inside the ball, to increase, and that is going to lead to an increase in volume. So Charles' law said that volume is directly proportional to absolute temperature. Now, if you leave a soccer ball outside, then you expect that the heat from the sun is going to cause the temperature of the gas inside the ball to increase, which is going to lead to an increase in volume of the ball, and that's why it will tend to look as if it is full. I would like to believe that you enjoyed watching this video and that there is a lot that you learned that you will be able to apply when you write paper 2 of physical sciences this year in grade 11. Goodbye. I will see you in the next video where I will be continuing with ideal gas laws and thermal properties. Goodbye.